Hey, what's up YouTube? I wanted to make a fourth and final video to conclude this little boat simulation adventure of mine, because there are a few things I left out in the 3 previous videos, and I would also like to talk about an attempt at making a simplified wave propagation system. So without further ado, let's dive right into it. A few people asked me how I implemented controls for that boat, so I guess I'll start with that. First, I used UEFI's Enhanced Input System. It's meant to replace the legacy input system, so better get familiar with it now before Epic gets rid of the legacy system for good, right? All in all, for simple use cases, well, it's quite simple. First, you probably want to make sure you have that plugin enabled, and that you have this enhanced player input set in your project settings as a default input class, but as far as I know, that should be true by default in any UEFI project. Now for this project, I just needed to move that boat around in 2 dimensions. I didn't need to move the camera around because it was meant to be a fixed top-down view, right? And so I just had to create a single input action. I just had to make sure it's set to 2D axis. Then I created an input mapping context, added a mapping, and made it point to that input action asset. Next I added as many inputs as I wanted to move that boat around. So WSAD for keyboard controls, left and right triggers, and left thumbstick x-axis for gamepad controls. For that first W key, I had nothing to do here. That key is meant to add a positive value in the 2D input vector's x component, and it does that by default. For the S key, I just needed to add a modifier to negate that x value. Then for both A and D, I needed to add a swizzle modifier. Those 2 keys are meant to add positive and negative values in the 2D input vector's y component, so swizzle does that, right? It swaps the x component with the y component. And for the A key, I also needed to add a negate modifier to, well, send a negative y value. For triggers, it's the same idea. Left trigger to brake, so I added a negate modifier, right trigger to accelerate, so the default settings were correct, and the thumbstick x-axis to turn, so again I just added a swizzle modifier to swap that input vector x component with the y component. Once that was set up, well, there are many solutions to this next step, which involve getting the player controller, getting its enhanced input system to add this mapping context. Doing that upon begin play in the pawn blueprint is usually a decent place to do so, but you do you. Last step was to add an event for that input action. It should show up if you search for its name in the search bar. Voila, upon trigger, I then had access to that input 2D vector to move the boat forward and backward and rotate it, which shouldn't happen if the boat is airborne, obviously. Would be weird to be able to control it when it's not in the water, right? So I have that motor submerged value, which acts as an overall multiplier for those 2 input axes. And that motor submerged value is just an average of the depth at those 2 pontoons at the back of the boat. So if those 2 pontoons are submerged enough, I consider the motor, which is supposedly around that location, right, to be submerged enough, and that allows me to control the boat. I apply a linear force to go forward and backward, and torque to rotate the boat around. For the linear force, I first get the boat's linear speed to check if it doesn't exceed a maximum speed limit. If it has, well, actually I could be currently moving forward at max speed and willing to brake. Or the other way around, I could be going in reverse at max speed and willing to accelerate. And so that's what I check with that sign test here. If it's all good, I just add a force in local space relative to this boat, right? It's slightly offset to get the desired behavior though, like have that boat tilt upward a bit upon accelerating. To turn, well, again I apply a simple torque, and you might want to turn this axle option on for this torque force to have a strong enough effect. Here I made the arbitrary choice that I wouldn't be able to rotate the boat if it wasn't moving forward or backward, which sounds right to me. It's not like I have driven a real boat before, but I assume a boat would have to have some kind of linear momentum for it to turn, so I check that. Get its speed along its forward axis, normalize it based on the max allowed speed, so I can turn harder the faster I go. And that's pretty much it for controls. Now that force-driven movement approach obviously only works because my buoyancy system makes this boat be physically simulated. It wouldn't work on a non-simulated actor, right? Next topic is the water shader. I got a few things to say about it, so let's dive right into it. Okay, first of all, it's always great to make your life easier by making assumptions. Meaning I knew from the get-go that I wanted a fixed top-down camera. Getting things to look good at any camera distance and angle is the most time-consuming thing ever, obviously, and I only can spend so much time on these Patreon projects and YouTube videos, so I try to simplify my life as much as I can. And going with a fixed top-down camera definitely did that. For one, it drastically simplified the way I could build the water mesh. Remember this previous video I made about a Screenspace grid? Well, a top-down camera is a perfect candidate for such technique. This water mesh is a Screenspace grid, which has its fair share of issues. First of all, get close enough to the water and you get this strong aliasing issue I explained in that video, right? Moreover, using a Screenspace grid technique, well, there are a few edge cases to handle, namely going below the virtual plane, meaning going below the water surface. Here, well, I didn't handle that case, so the mesh goes nuts. But still, a top-down camera and a Screenspace grid, yes, best use case. It allowed me to have a very decently tessellated water mesh for very cheap, and because it's in Screenspace, it follows my pawn around. That's one thing. Now onto the water shader itself. First of all, that water is not as cool looking as I would have liked, but then again I had limited time to work on it. It lacks foam, some wave crest treatment, with splashes and whatnot, but I suppose it got the job done for this little demo. So this water shader is a mix of techniques. There's one used to create large wave motion, another technique to create medium wave motion, and another technique to create details wave, if I may say. So large waves are created using Gersner waves. I generate only 8 waves, so it's actually quite cheap. And that's where the main wave motion comes from, and so that's what's sampled in my buoyancy system to get the boat well floating. The second wave technique I used is that FFT flipbook method I explained in a previous video. So I used a height flipbook to add some extra vertical displacement, which is kept subtle enough to not participate as much to the final water height, so the buoyancy system can pretty much just skip that extra displacement, right? And I also used a normal flipbook to add extra normal details. The third and last wave technique is very simple, I just used a basic static water normal map. And that static normal map texture, because projected in world space before world position offset is applied, well, it gets deformed, like stretched and squashed, once that Gersner wave offset is applied. Same goes for that normal flipbook, by the way. Speaking of which, I also add an extra layer of deformation based on that FFT flipbook normal, so that static texture is doubly stretched and squashed. Once by the Gersner wave offset and once by the normal flipbook to slightly distort UVs. So it's a static texture, sure, but in the end it does the job just fine to add extra finer details, and it doesn't look that static because there's enough wave motion to distort it in all kind of ways, right? Now I feel like I mentioned this a lot in previous videos, but Gersner waves come with a catch. Vertices are displaced not only in Z, but also in X and Y. Which is great when you want to project, say, a foam texture and have that foam texture stretch and squash with the waves, right? That's what gives this believable water behavior after all. However, this feature can go against you, like here. This is a captured foam texture. Feel free to watch part 2 if you haven't already, else this probably won't make any sense. Anyway, you see, I had a dilemma with the way I'd project that texture. Because that foam capture happens in world space, right? And so whatever emits foam at a given world position, once projected onto the water surface, which is offset both vertically and horizontally, well, may not actually be properly positioned anymore, if that makes sense. One obvious way to fix this is to project that foam texture only once the water surface is displaced. But then it's no longer stretched and squashed with the waves, and that creates some kind of disconnection, right? Like it doesn't feel like this foam is actually sitting on top of that moving water. And I don't believe there's a simple solution to this, but maybe I overlooked something and then I eventually ran out of time to try the few ideas I had. I'm sure there are solutions though. Water is definitely a rabbit hole, but anyway, that's the water shader in a nutshell. Now, I briefly want to mention a common issue when rendering a boat on top of a displaced water surface. That boat may be concave and you might want to hide water inside it, obviously. And there are many techniques to do so, let me show you a couple. Probably the most common solution is to rely on custom depths. First, I modeled what I called a cap mesh. Then in this blueprint, I added that basic boat mesh and its cap. That cap mesh has to be a separate static mesh because it has to be configured to not be visible at all to anything except to the custom depth buffer. That buffer, right? By the way, you may want to make sure it's enabled in your project settings. Then in my translucent water material, emphasize on translucent, it's important, I can then mask out the water if the custom depth is smaller than the pixel depth. It basically means that cap mesh is closer to the camera along the camera's forward axis than the water surface is, so obviously water should be occluded at that pixel. And that's a very handy technique. One limitation, however, is that the water surface might be displaced enough so that it ends up above that cap mesh, and so it becomes visible again, right? Second technique, that one is way simpler but only works if you use a single layer water shading model. So forget about that depth buffer thing, right? All you have to do here is to create that same sort of cap mesh again and assign it a material that also uses a single layer water shading model, but making entirely transparent. And voila! Same issue than before though, water might be visible if displaced enough to be above that cap mesh. But actually there's a trick. You can shift that cap mesh vertices towards the camera using a simple world position offset logic, like so. That gives you some extra safety margin before the water gets above that cap mesh, if that makes sense. Third one is actually really similar in principle to the first one. However, instead of relying on custom depths on a cap mesh, the idea is to project a cap texture onto a virtual plane that matches this boat's transform directly in the water shader. So here I have a material parameter collection with a few vector 4 parameters. One to store a location, a scale, a forward and a right axis. In that boat blueprint I then have a vector variable with that widget option turned on, so that I can set that virtual plane's location right about here. Then I transform that vector, which is an offset, from local to world space and forward that to the material parameter collection. I also forward this actor scale, forward and right axis. In my water material, I can then get those vectors and make use of that function to create a virtual plane onto which I project that cap texture. However, this is UI's built-in virtual plane function and I don't really like it. So I copied the logic I was interested in, mostly the math to compute the virtual plane intersection, to create my own function. This bit of math pretty much just shoots a ray and tries to find the intersection point given a ray start position, a ray direction, and a plane position and normal. Actually, I've explained in details how this virtual plane function works in that Screenspace grid video of mine, so you might want to have a look at it for more information. Anyway, from that intersection position computed at each pixel, convert that XYZ position into UV coordinates using two given axes. UI's built-in function can derive orthogonal vectors and whatnot, but personally when I have a use for that virtual plane function, I pretty much always have a complete set of normalized axes on hand, like here. That boat's forward and right axis, and the remaining third axis is derived using a cross product, nothing fancy. So I could simplify a lot this built-in function when creating my own by assuming an x, y and z normalized vector would be provided by the user. Anyway, then here use those UV coordinates to map a texture onto that virtual plane, and then optionally create a box mask to well mask that texture, so that it only tiles once or twice, you get the idea, it's a box mask. And then I added an extra bit of logic here to support a two-sided virtual plane, because it's actually a feature I need here in case the boat tips over. If that happens, obviously that cap texture shouldn't be visible anymore, right? And that's done with a simple dot product to see if the camera sees the back face of that virtual plane. And that's how, in a way, this method allows you to rebuild a sort of custom depth directly in a shader, without actually rendering a flat mesh into the custom depth buffer, and thus cheaply create a boat mask, which is neat. The thing you might like or dislike about that method is that the water is now always masked regardless of how much that boat is underwater. And finally, that virtual plane projection method brings me to the last chapter of this video. It might not be obvious at first as to why this is related, but bear with me. One thing I tried with this boat simulation was not only to generate splashes and foam, but also to have the boat interact with the water. You see, almost 2 years ago now, I released this advanced wave propagation system, emphasize on advanced. It doesn't do everything, but it does quite a lot, certainly a lot more than what I needed for this small boat project. Plus it relies on a scene capture component, and I already had one for the foam capture, so I really wasn't looking into having one more. I have a love-hate relationship with scene capture components. They are great, but they cost so much. Anyway, so I actually built a much more minimalist version of this wave system, one that doesn't involve any scene capture component. It's however now quite limited, but while working on it I thought it could be a nice educative resource for you guys to have, so I thought hey, why not release it and make a quick video about it as well. Especially because it makes use of a neat trick, so I'm eager to briefly explain its inner workings. Alright, so it comes in the form of a plugin, which contains a single blueprint component. Blueprint component meant to be added to your controller blueprint. It also has a material function meant to be used in your water shader to sample the wave height and normal. That material function, however, makes use of a material parameter collection, so be aware of that. You may reach the 2 collections limit per material. In that case, you might want to merge multiple collections into one. That material parameter collection is used to get the wave capture coordinates to project those 2 render targets, one for the wave height and one for the wave normal. Now, I won't go over too many details because this minimalist wave system is, after all, just that, a minimalist version of this advanced system, so it makes use of techniques I already explained in the video dedicated to this advanced system. Just know that it uses the same wave propagation algorithm you can find in the content example, and the same local to world projection technique I explained in the second video of this boat simulation series. The only particular thing about it, and the trick I actually wanted to explain, is how I compute the what I called intersection map to detect where that boat, well, intersects with the water. It's in principle a very similar challenge I faced when building my foam capture system. But that foam system used a scene capture component to achieve that, and that's precisely what I try to avoid with this simplified wave system. So how does it work then? Well, in 2 words, virtual plane. See, told you that chapter had something to do with that virtual plane material function. By having a virtual plane matching that boat's location and orientation, I could first project that boat's profile as a texture onto that virtual plane, then sample the wave height and compare it with this virtual plane's height to create some kind of vertical gradient and create an intersection map. And so that's what I'm doing in this material. First, compute the wave height. Here this demo has a simple water shader that makes use of Gaussian waves, so sample waves with the same exact parameters to get a matching wave height. Send that wave height, the boat's location, axis and scale to that material function that first creates a virtual plane, and then compares that plane's z location with the wave height. And that's how close this boat's planar profile is to the water. And that's the material rendered into a render target to create this intersection map. Kinda cool, huh? Now there's an elephant in the room. I previously showed a material function called something something virtual plane, yet this one is named virtual plane ortho. Ortho for orthographic, and that's quite important. You see, when rendering a material into a render target, well, there's not really any camera, right? There's no camera position, and there's actually no perspective either. Yet, this virtual plane function uses the camera to compute a redirection at a given pixel. And when rendered into a render target, well, it just doesn't work. So I need a method to generate a virtual plane with a made-up orthographic camera, which is, thankfully, straightforward enough. Instead of computing a redirection from the camera's position and world position, well, I provide a made-up direction. And an orthographic camera really just means that redirection is the same everywhere for every pixel. That's what gets rid of the perspective, right? And so that simplifies the process even more. I really just have to use that specified direction and that's it. Also that bit here, to compute the two-sided plane logic, has to be updated as well, but it's no big deal. And voila, here's a virtual plane matching that boat's transform, computed from a made-up top-down orthographic camera and rendered into a render target. Just have to sample the wave height and compare it with this plane's z location, and that's how I built that intersection map. It then gets injected in a wave propagation algorithm, which again you can find in the content examples for free, and in my wave propagation system, available at tier 3 reward on my Patreon. Then I apply a local to world transform to make this wave system boundless, just like I explained in my foam capture system breakdown video, so I'm glancing over the rest because it should be familiar to you already if you have followed my YouTube channel for some time. If you haven't, welcome aboard, pleased to meet you, feel free to leave a like and subscribe to the channel if you like this kind of content. Finally, the reason I didn't include this wave system in my boat simulation after all. There are a few actually. First, the sense of scale was quite impossible to get right. It just didn't look right. Although that kind of wave propagation algorithm is very naive. And realistically, on a water that intense, with so many waves already, those interactive waves should probably propagate in a very chaotic way, merely just adding extra chaos to an already chaotic water, and this system obviously doesn't allow that kind of behavior at all. It's again very naive, and having that kind of wave very smoothly propagating on that chaotic water looked just wrong. I'm sure it could be improved though, but again, time constraints, right? Although, just like with that foam texture, I had the same dilemma with the way I would project that wave displacement and normal map on the water surface. Either it be displaced by Gersner waves, thus looking somewhat connected to the water if I may say, but potentially propagating from an incorrect world position. Or not displaced by Gersner waves, and thus creating an even stronger sense of disconnection between those waves and the water surface, if that makes sense. Plus, in the end, the star of the show was that splash system, wouldn't you agree? So why not let that splash system have some spotlight, right? And with those very poetic words, I think I will conclude this boat simulation adventure of mine. I hope you enjoyed this little series and that you learned a few things along the way. If you didn't, well, I at least hope it was entertaining, and I thank you for watching. As usual, feel free to leave a like and subscribe to the channel so you don't miss on any upcoming videos. Also, consider joining my Patreon to support me and if you want to see more content like this. That much simplified wave system is available as a tier 2 reward in case you want to take a look at it. Again, it's quite limited, as is it can only render the intersection map of a single actor, so I really see this as an educational resource more than an actual complete system you can use, right? But I will let you be the judge of that. I also released a super duper simple example of my virtual plane function, both the non-orthographic version and the orthographic version with a tiny demo level as a tier 1 reward. Anyway, I already am working on the next projects and videos, plural, so stay tuned. In the meantime, take care of yourself and I'll see you in the next video. Bye bye!